So after Safer's talk last month, today we'll continue our discussion on model bias and predictability. So it's a great pleasure that we have Professor Žagar with us today to present her work and lead our discussion. Nedjeljka Žagar received her bachelor degree in physics and a master's degree in atmospheric physics from University of Zagreb. She has spent 7 years working on operational weather forecast before she went to Stockholm University and pursued her PhD in dynamical meteorology from 2000 to 2004. After her ASP postdoc at NCAR in 2007 and 8, Nedjeljka went back to Slovenia and worked as assistant professor, associate professor, then a full professor at University of Ljubljana. She just moved to Hamburg last year as a professor of theoretical meteorology at University of Hamburg. Her research covers large-scale atmospheric variability, tropical dynamics, atmospheric modeling, data simulation, and predictability. So today she's going to talk about assessment of scale-dependent variability and bias in global prediction models. So good evening, Nedjeljka, and the floor is yours.
Thank you so much, Hayan, for this introduction and for the invitation to give a talk to this panel. And good evening from Hamburg, everybody. It's an honor for me to speak tonight or today for you. So I will focus on scale dependency of global variability, which means variability as a function of the zonal wave number or the global wave number. It is more common to look at variability for a single variable, a single level or region, or look at zonally average state. Complementary to this, I will discuss global variability in modal space, which is the space defined by multivariate spectral decomposition. Linear wave theory, which is behind this, provides variability split into two dominant types of flow, balanced or quasi-geostrophic or Rossby regime, and the rest, which we call unbalanced regime. And so first I will present the method, and once the method is introduced, I will present a few results from 2 recent papers with my students and postdocs. In these papers, we quantify variability across scales in reanalysis data. We quantify uncertainties. We validate variability simulated by a climate model, and we try to suggest a way forward for understanding how simulated variability is coupled to model biases. So this slide lists 3 questions that this seminar will answer. The first question is whether we can formulate a global measure of circulation variability accounting for dynamical regimes, and the answer is yes, and we can use linear wave theory as a suitable tool for this purpose. The second question is whether we can detect in wave number space relatively small changes in mid-latitude Rossby wave variability and equatorial wave variability. The answer is yes, we can, and I will show results regarding this from a recently published Journal of Climate paper. The third question is on uncertainty quantification. I'm asking to what extent the 4 major reanalyses agree on the sign of recent trends. And the answer is that they agree regarding the Rossby waves in summer and the most energetic equatorial waves, but they disagree about the rest of unbalanced circulation, which mainly belongs to the tropics. So to start with, of course, I'm showing some movies, and these 2 movies show December last year, and they illustrate 2 dynamical regimes, meandering westerlies in the extratropics and these slowly changing weak zonal winds near the equator. And if you look at the title of this tropical movie, it says balanced because this movie, the zonal winds there are only those with the winds quasi-geostrophically coupled to the temperature field, and this has to be complemented in the tropics by a faster component, unbalanced component, which is made of Kelvin waves, which are shown in this movie on the left. And again, it's a Kelvin wave zonal wind in the longitude pressure cross-section along the equator, averaged plus minus 10 degrees of the equator. So two things in this movie can be noticed. One is the tilt with height, and another one is the vertical wave propagation. And to illustrate the second one, I just put the Kelvin waves at 4 subsequent 24-hour apart times. And I put 2 horizontal lines, one at around 70 hectopascals and another at around 115 hectopascals, just to illustrate how the phase of the wave moves downward, which is telling us that the energy is propagating upward. And I deliberately picked the Kelvin wave as the best example of how the linear wave theory can be used to filter individual modes of variability. So here I'm once again showing Kelvin wave, but its horizontal structure along with few other modes. And the decomposition which is applied is, of course, known to everybody. It is a normal mode function decomposition. And over the past decade, actually starting with my ASP postdoc at NCAR, I worked on this decomposition to create this mode software. But the foundation and theoretical foundation and development of this decomposition go to 70s and 80s at NCAR, and the work by Dr. Akira Kasahara and his collaborators. And I was very lucky and honored to have NCAR scientists as my hosts and supervisors during my ASP postdoc. So I've been using this, and the result of the modal decomposition at a single time step is this complex half expansion coefficient chi, which defines both wind and height perturbations associated with a specific zonal wave number, meridional mode index, and vertical mode index. And these modes are orthogonal, so we can do all statistics on the time series of these complex numbers, half expansion coefficients. We can compute energy at a single time step. Then if I average energy over the time window, I get time averaged energy spectra, and that is this capital I with overbar. I can also average these spectral coefficients, and then I get the time average signal or the mean state. And then I can compute its energy. And I compute deviations with respect to this time average signal, and I average it in time, and this is variance, sometimes called transient energy. And under the assumption that the time and space averages are the same, if we have sufficient amount of information, we have this equation which couples spatial and temporal variability, which is saying that the difference between the spatial variance and temporal, and half of the temporal variance is equal to the spatial variance of the mean state. And it can be shown, it's actually easy to show, but we demonstrated in few papers that this variance in modal space, which is shown here, is equivalent to the variance in physical space, in grid point space, where we sum up variances for the zonal wind, for the meridional wind, and for the geopotential height, which is weighted by this factor G over D. So I will not go into details, but I just want to point out that this whole statistics in modal space is equivalent to the statistics of circulation in physical space. Here I show two examples of spatial variance, or the total energy spectra, which are decomposed into Rossby, which is the red spectrum, or balanced energy, and unbalanced or IG modes, which is the blue spectrum. And their sum is the black spectrum, which is the total energy. So regime, and what this shows, this demonstrates this regime decomposition, which we get from the linear wave theory. And the regime decomposition is more commonly presented for kinetic energy using irrotational and non-divergent paths and the Helmholtz decomposition theorem. The difference here is that the spectra which I show, they include the available potential energy. And another difference is that the large-scale tropical modes, which I'm very much interested in, such as the Kelvin wave I showed earlier, they are here fully part of the blue spectrum, of the unbalanced spectrum, while in the vorticity divergence decomposition, they end partly in irrotational and partly in non-divergent kinetic energy. So so this method is particularly suitable for looking at the tropics. So if we compare these two plots, maybe interesting difference between them is that the left one, which is the operational ECMWF model from recent winter, has the Rossby spectrum, which follows -3 slope all the way to the smallest scale, while the reanalyses, which are produced with an older version of the model, they have more steep balanced spectra and also more steep the total spectra, simply saying that reanalyses underestimate spatial variability at subsynoptic scales. Now I stay now here in the figure in the left. I stay with spatial variability, but the other two figures are showing temporal variability. So and this is to remind you of this relationship between the spatial and temporal variability. So here I'm averaging total energy spectra over 30 years of ERA interim data in June, July, August season. And then the spectra on the right shows subseasonal variance in the same season and data in two ways. One way is as a function of the zonal wave number. And another way, figure on the right, is variance as a function of the global wave number. If I integrate both figures, it is exactly the same, but I'm showing this to illustrate the advantage of using the global wave number, in which case the tropical variances end in these lowest global wave numbers. And you can see, for example, global wave number 1 in this representation has more subseasonal variance in the unbalanced circulation than in the balanced circulation, which has to do with the large scale variability in tropical, both upper troposphere and the stratosphere. Okay, so if I stay with subseasonal variability, now I would like to discuss its uncertainties in 4 major reanalysis data sets in the tropics and the extratropics. So this is shown in these two figures. And the top panel shows time series from 4 reanalysis data of subseasonal variability deviations. So for every season, I compute subseasonal global integral of subseasonal variability. In top figure, this is the traveling Rossby wave 6. And so for that particular season, I take difference between this season and the 30-year average of subseasonal variability for this particular season. So, and then I normalize this to get these deviations as percentages. So what you see that the traveling Rossby waves are very similarly very well represented by all four reanalyses. That I guess does not surprise you. But then the bottom figure is showing the same deviations, but for the sum of the three main large-scale equatorial waves, which is the Kelvin wave, the mixed Rossby gravity wave, and the westward propagating inertia gravity wave with the lowest index, and for the wave numbers 1 to 5 and the mean zonal state for those. So in this case, you can see that differences among four reanalyses are greater. Not all the time, but often. And then something common in both these plots, which can be seen by eye inspection, is that in case of traveling Rossby wave number 6, we see mainly negative deviations in the last decade. And for the tropics, for the tropical modes, we see mainly positive deviations in the last decade. So so this is suggesting that the reanalysis should agree on both these signals, and they indeed do, but for the unbalanced circulation, they agree only for these dominant signals in the tropics. And this I illustrate here by comparing era 5 and era interim. So this is the comparison. So what is plotted here is the change in variance over this 35-year period after we do this linear fit. And crosses indicate statistically significant change. So here you see at the bottom of this era 5 4 plots the large scales and this mode 0, which is the Kelvin and mixed Rossby gravity and westward IG mode. That they are red. This is what we have seen in time series figure, but the rest of the subseasonal variability is blue and mainly statistically significant, which means a negative trend, while era interim has a positive trend overall. And if I add two other reanalyses, MERA is most similar to era 5. And GRA 55 is more similar to era interim. So, but the main conclusion here is that they do agree for these really leading, most energetic modes of variability. So now the same figure for the extratropics, not exactly extratropics, but for the Rossby waves. So if you look at two summer seasons, JA and December, January, February, you see that in both of them we have statistically significant reduction in zonal wave number 6, which I showed earlier in time series. And at the same time, we have the statistically significant increase in subseasonal variability at several lowest or quasi-stationary Rossby waves. So this signal is stronger in era interim JRA than in era 5, but the reanalyses do agree. And this trend is consistent with the quasi-resonant amplification mechanism, which was proposed by Petukov and collaborators here in Germany as a mechanism for the persistency of extreme weather events in mid-latitudes. So both these results were from a recent paper in Journal of Climate. And now in this second part of my talk, I would like to discuss how this same modal framework can help us to better understand how biases lead to deficiencies in simulated variability by climate models. And I will also try to demonstrate how scale filtering of biases can inform us about bias coupling in different regions this is also my group ongoing research topic and something I call bias teleconnections. But let's first define the bias in modal space. So now I have reanalysis as a proxy of truth. I stay at large scales where they do agree, in extra tropics certainly. And then I have my climate model expansion and reanalysis expansion. And then I take the time average of differences between reanalysis and climate models. And if differences are random, the time average should be 0. If they are not, this is what we call bias. So, and this is a complex number, which then can be used to filter any scale or regime back to physical space. And this is what I'm showing here. So this top plot is a zonal wind and temperature biases in winter, in boreal winter, in wave number 1, along a single latitude circle in subtropics. So, for example, what is this saying? This is saying that the positive temperature biases in this model, this is really a simplified climate model called SPEEDY, and it is run here for 20th century, forced by the observed SST from era 20th century reanalysis, and then validated with this era 20th century reanalysis. So, and this suggests that near surface biases in temperature are coupled to the over Pacific, are coupled to the upper troposphere biases in temperature, positive again, over Atlantic or Africa, and similar for the negative biases in temperature in another hemisphere. And these biases, for example, are once again shown here in the bottom 4 plots, where I filter zonal wave numbers 1 and 2 for the U and V winds at a level, and I show the level around 100 hectopascals. So what you can see here is that in this particular model in winter, these biases originating from the tropics, the tropical biases are coupled to the biases in the extratropics, really half a world away, zonally and north. So with this bias evaluated, we can compute the spectrum of the bias, which I call bias variance and denote by B. And then I can apply this relationship between the spatial and temporal variability to the model and to the reanalysis. And I express the model as the analysis plus bias and work through a little bit to get this relationship, which is framed in this blue frame. And it says that difference between deficiencies in spatial variability and deficiencies in temporal variability, which is equal to deficiencies in the simulated mean state, can be represented as a sum of the two terms which represent the phase and amplitude of the bias. This B term, which I call bias variance, and this covariance term, which I denote by P, and it is simply the covariance between the truth, between reanalysis and the bias. And I would like to illustrate you the importance of these two terms by a very simple example. So I have a truth which is defined as a wave, and then I have my climate model, which does a great job in simulating the amplitude. So I assume here that the amplitude is right, but the phase is not. So I have phase shift delta phi. And then I work through, so I want to evaluate total bias. So I evaluate first the bias, which is given by this relationship. Then I evaluate bias variance, bias covariance. And the total bias, which is half of B plus P, is given by this bottom equation. So we see here that the total bias depends on the phase shift of simulated wave with respect to reanalysis. So if the shift is 0, the total bias is 0, everything is perfect. But if the shift is pi, or the wave is out of phase, then I have bias which is really very, very much larger than the variability. So I have the perfect variance spectrum, but my model is really very poor, and my bias really 4 times exceeds variability. So now towards implementation of this way to evaluate climate models, we looked at the coupling between the missing variance in this simplified climate model and the bias, and that is what is shown in this figure. So let me explain what's shown here. So there are 3 plots. In the first one, we have the climate model with the model force with observed SST. So this is EMIP-like run, and the model is evaluated with the era 20th century reanalysis. In the middle panel, I have now what I call coupled run, where the model has own coupled ocean model, which is very simple. It's a slab ocean, but but I call it coupled run, and I still evaluate this with reanalysis. And in the third panel to the right, I have what I call perfect model scenario. In this case, I evaluate coupled model with the EMIP run. So the atmosphere is perfect, or perfect atmosphere model scenario. Then what are different colors? Different colors belong to different seasons, which you can see in this legend. And the black is the annual value, because this is 20th century simulation. And what are different dots? So going from the top down, different dots belong to different wave numbers, because the variance and the bias, they both have a red spectrum. So the top 5 numbers, they belong to the zonal mean state. And then as I go down, every next set of these five dots correspond to 1 zonal wave higher. So I hope this is clear. Then you see that mainly x-axis is negative, which means that my climate model is underestimated variability, which is very much expected, because this is T30 climate model, and era 20th century was prepared with much higher horizontal and vertical resolution, and much, of course, its reanalysis. So what you see, for example, here in this area, once I reach a wave number around 15, I increasingly lack more and more variance. And the biases, another thing to notice here is that, and there is a larger spread among seasons in a missing variability in the model, and this has to do with the way how the model simply redistributes energy in order to adjust to the model works. The energy transfers in the model work to adjust the variability spectrum to these biases. Then in the coupled run, these top 5 dots, they are much greater now, because when the model is run without own ocean model, the biases greatly increase, especially in the mean zonal state, because it's a poor ocean model. But then when I have the perfect atmosphere model, which basically resolves all scales, this time you see that I really, my portion of missing variance is much smaller. So I do have sufficient amplitude of variability in the model at all scales, but these large biases here at the top, they are not reduced. So meaning that if we have the poor ocean model, even the perfect atmosphere model, we will produce small scale variance, but cannot really improve the large scales in the atmosphere. Okay, so with this, I would like to summarize, and I have split my summary in 3 points. So first, I discussed the physical framework for the description of atmospheric variability and climate model validation. And this framework quantifies variability and biases across scales for the 2 main circulation regimes. And this is most useful decomposition in the tropics. The framework is suggested as a way to understand how biases affect simulated variability in remote regions of the atmosphere. And this is really the topic where my group we are going to work in the next period towards implementation of this kind of diagnostics in a full climate model. Then I showed that reanalyses agree on summer trends in extratropical troposphere, tropospheric Rossby wave, and on the trends in most energetic signals in the tropics. So once again, I find this most informative for the tropics because we could see that the known uncertainties in our understanding of tropical dynamics and the lack of wind observations and the focus, of course, of all data assimilation schemes on the medium range extratropical forecasts makes or keeps making tropical analysis a critical point of global circulation. Okay, thank you very much, and I'm very much looking forward to discussing now.
Thank you. Reminder, if you have a question, use the raise your hand button, which is found next to your name, or you can type your question into the chat box.
Shall I, Jenny, shall I stop sharing screen now?
If you would like to, yes. If there are slides that you want to refer to, you can always reshare.
Yeah, great.
So any questions?
Hi, Joe.
Hi, I have one question. In your summary slide, in the last point, you mentioned the reanalysis have better agreement in the balanced part, but the unbalanced part shows larger differences. So my first question is, theoretically speaking, what constraint do we have for the unbalanced part of the circulation? And the second question is, if we link the unbalanced circulation to convection, the unbalanced circulation in the tropics can also be linked to like a Rossby wave response in mid-latitudes or extropics. So do you see like biases in like in the balanced part of the circulation in extropics related to the unbalanced part of the circulation in the tropics? I don't know if I made it clear.
Yes, I hope I understood, because these exactly the same questions. I am asking exactly these questions, I think. Yes, we, for example, with my student Katarina Kosovel, we looked at using the same decomposition framework. We looked at how perturbations in tropical diabatic heating, for example, associated with MJO, propagate, project, what modes they project onto, and how this propagates out from the tropics. And of course, this is very much studied subject. But the difference in Katarina's work was that she applied the fully non-linear moist simulations. So she was able to show how moisture feedbacks amplify these perturbations and also amplified the response to them, especially in the Kelvin waves, and then also in the in the divergence generation in the subtropics. So I cannot answer your question on direct coupling between unbalanced tropical representation of unbalanced tropical circulation and extratropical predictability, because this is exactly what for example, what we are now discussing with Jeff and Kevin as a focus of our hopefully next collaborative effort to look exactly at these multivariate couplings between the in the tropics and see what their impact on extratropical predictability. Yeah. Sorry, I can't give you really answer.
Thank you. For my first question, see if we want to better constrain the unbalanced circulation, in which direction should we go? What are the possible directions?
Yeah, so here I could actually, of course, the signal, the unbalanced circulation makes a smaller part of total circulation. Let me just show you one figure here, which I will just share screen again. Yeah. So I hope you can see this slide. And it is showing the portion of variability, so the square root of the variance as a function of the zonal wave number in 4 reanalyses in summer season. Okay. So we see that, of course, it is the smaller, and then in variance it's still square of this number. So it's really a small part of the variance. But once we come to wave number 35, so we move to subsynoptic scales, this part becomes dominant. The reason, and here you also see the differences between 4 reanalyses, and the reasons for this are, of course, that the multivariate, that the balancing procedures which are part of data assimilation, they don't really provide coupling between the mass and wind field in the tropics. And together with the lack of direct wind observations, we cannot constrain then sufficiently well tropical circulation. And as a proof of this uncertainty, I can maybe advertise next week is a CalVal, which means a calibration validation workshop of European Space Agency satellite Aeolus. That's the first satellite that's the first Doppler wind LiDAR in space, which is measuring line of sight wind profiles. And due to the lower than planned power of the laser, there are large random errors. So observation error of these data is 5 to 6 to 7 meters per second. And in spite of this large random error, these observations have been shown already by all major NWP centers that assimilate them in Europe to substantially reduce effect or improve tropical analysis and forecasts. And this, I think, is telling us that we really have these uncertainties in the tropics. And the largest effect of this new wind data is in the upper tropical troposphere, right under the tropopause and right above the tropopause.
Okay, interesting. Thank you.
Any other questions?
Nedjeljka, you showed a picture that there's a reduction of wave number 6 variance. I think in Petticoat's group publications, they emphasize the wave number 6. Is there a contradiction?
Can you please say again what publication do you refer
I
to?
remember Petticoat's group, Como, they emphasized there is an increase of variance at wave number 6, and there is a resonance, increasing resonance at wave number 6, and but in your analysis, you showed there is a reduction of variance at wave number 6. So I also wonder. So in your plot, there is what caused the reduced variance at wave number 6? Do you have any further comments?
No, I just mentioned that. I mean, I think this reduction, along with an increase at quasi-stationary Rossby wave, this is in agreement with the quasi-resonant amplification and with with an increase in situations like blockings, like heat waves in summer. So this is consistent with what Petukov and also Mann and several others have been discussing in last years. I mean, they do report this for the wave numbers 6 and 7, I think. And we see it here really kind of mainly focused on wave number 6, and as you can see, statistical significance is not found all the time in all meridional modes. But this y-axis, these meridional modes, you can think of them as the meridional wave numbers, and the higher the mode, the more extratropical signal is. So I think this is consistent. It's just that it's really focused in our analysis on wave number 6, and in wave number 7 it's neutral really.
Okay.
I think we have a question from Matt Newman. Go ahead.
Let's see here.
So you're muted. There we go.
Sorry, I'm not used to using WebEx. Unfortunately, I missed the first few minutes, so this is maybe a ridiculous question as a result. But you're talking about Huff modes, right? That was what you were saying? So these are, when you say linearized, you mean linearized around a state at rest, or?
Yes, the linearized modes, I follow the modes, completely follow the work of Akira Kasahara at NCAR. So
Right.
the horizontal structures are derived with respect to the state of rest.
Right.
This said, we are using only the spatial structures of these modes for the projection at individual time steps. So when I look at the time series of this data, like in the movie, I show. Let me just, if you missed the beginning of the talk, I would like to share this screen again, because I
saw that.
So you see these Kelvin modes. I mean, we do not make use of the phase speed, of the dispersion relationship for Kelvin of any other mode, but the fact that that when we simply cut together these signals, which are independently analyzed at subsequent time steps, we still see some coherent propagation of the signal in time. So yes.
I guess my question is whether. So I don't quite see how you are taking into account. Maybe again I missed this. How you take into account the strong zonal and meridional, not to mention temporal variation in the basic state, which certainly in the exotropics, and I would argue even in the tropics, pretty much controls to a substantial degree the way the waves evolve and interact with each other in a way which I'm not even sure a normal modal decomposition is entirely representative of the real system. So I'm struggling, I have to admit, with trying to understand how one could take this sort of approach, and maybe there's a way. That's why I'm asking the question. You could take this sort of approach and answer a question, for example, I know that there are mean biases in the jets in the springtime and summer in almost every GCM, which has a big impact on Rossby wave propagation. And I know there are biases in every coupled model without exception in terms of the horizontal extent of ENSO and how those kind of errors could be influenced by mean errors either in the cold tongue or ITCZ or maybe something else, and how those errors impact predictions that are teleconnected to it in a way which are, again, very influenced by the zonal and meridional variations of the basic state. So in the tropopause and the troposphere, I kind of take it as an observational fact at this point that it's very difficult to do an analysis that ignores the variations that are driven largely by existences of the ocean in certain locations and the land in other locations, and that these control to a substantial degree the observed variability, and model errors must interact with how those effects are captured.
Yes, I can just repeat that I am simply projecting at a single time step data. This is a full projection, including the zonal mean state, onto these structure functions. And this is done independently at every time step. So for the large scales which we are looking at here, the shape of the meridional structure of the half functions is not, dramatically different due to the linearization with respect to the state of rest. So once again, I'm using these analytical structure functions as a projection basis, not for studying propagation properties.
Right, but I guess I'm missing the connection. That's what I'm asking. I'm trying to see what that tells us about the real atmosphere. How do biases in the models impact variability in the real atmosphere? How do these biases impact our estimates of predictability? Do you have a way that this approach can be used to answer those kind of questions?
That is what we aim at. So that's what I try to illustrate with. I don't have the full answer to this question. So with this relationship which I derive here, I am simply showing that if we have this decomposition into scales and modes, and the relationship between the variability, spatial-temporal variability and bias, we can just use it to understand these questions better, exactly the questions which you ask.
I am not sure my comment would help the discussion here, but I think I've read Nedjeljka's paper on comparing how the model, like different years, the error growth at different modes are different. Like I think you had a paper showing like comparing 2015 and 2018, like different modes, they have different error growths. So it's just a way to show, I think this is a kind of analysis framework to show error growth at different temporal and spatial scales.
Yeah, thank you. So I think you are referring to that predictability paper. Yeah, something which I did not discuss here. In that case as well, we are simply analyzing outputs of full model simulations using this linear decomposition. So we are not there looking at time-dependent growth in individual mode in time. So we are not forecasting amplitude in individual modes. We are just decomposing the outputs of numerical models. So you can think of this, what I presented, as a diagnostics.
Yeah. The thing last week at our last month, Safer's talk is focused on waveguide, wave training. If we simulate a bad jet, how that can lead to the error growth. And Nedjeljka's work is from more like a normal modes framework and using a different decomposition method to look at how the modes can help to organize the error growth.
Right. I guess my view of the troposphere is that a non-normal system is a much better representation. And so I'm struggling with how, and you know, the Žagar polynomials, you can, like you say, you could decompose everything in terms of spherical harmonics, and they're all orthogonal to each other, and they're all, you know, have certain characteristics, but I'm not sure how to relate that to a system where the dynamics are not normal. That's what I'm kind of struggling with. I mean, I appreciate what you're doing, and I take your point that it's a projection. So what I'm asking, especially for this, you know, for this panel where we are, you know, concerned with kind of real world prediction problems, is how do I relate that then to these other questions? That's what I don't.
So this will not directly answer your question. I would say this is rather one step forward compared to the composition in terms of spherical harmonics. And this is what I tried to discuss, that the spherical harmonics is a natural option because they are, for example, in models, in spectral models like PCMWF, they are the basis functions. But here what I discussed was that, for example, the variability spectra in terms of half harmonics, they provide a little bit more physical information useful for the tropics because few modes, at least, equatorial Kelvin modes and also equatorial Rossby modes, they are not sensitive to the shear. And this has been, for example, shown by John.
They exist. I think that's exactly the problem. Is that if you look at the tropics, I don't think they're entirely relevant either. They're useful in a WKB sense. So in a local, you can look at the mid-Pacific and tropical Pacific and say, okay, I have very much Kelvin wave-like behavior because I have a large domain where, in essentially a WKB sense, you can talk about Kelvin waves. But if you think of trying to have a wave that's propagating like the MJO, where it's going across the maritime continent, and where you have very different characteristics in the mean state, I don't know if that's as relevant. That's kind of the question. I mean, you could use, I guess you could take a step up and use generalized health functions. Have you tried looking into that? At least there you're starting to get a little bit of the shear into your basic state. I mean, eventually, if you use linearize around a time mean basic state, you know, your eigenmodes would not be normal. They would be very non-normal. You could not partition variability in the eigenmodes, right? You couldn't sum up across the eigenmodes in that way. And this is what I'm trying to get a sense of, is how do you relate what you've done in that in a very normal sense with what might be more representative of the physical system. So maybe you could, this is a question. I mean, I'm not saying I think you can. I'm saying I don't know how you do that.
I mean, these are the key questions. I think what you are basically asking what we learn by doing the spectral decomposition. Is this? I mean, basically, this is what you are questioning. So what we can, how to make use of a spectrum of whatever, you know, field, how to make use of wave frequency analysis in numerical models.
Not quite, but I mean, there's part of it.
Yeah, so I guess as a teacher, we teach everything we teach students.
I know. That's the problem. We teach students all the wrong things.
Thinking about how, you know, how difficult question you are asking. Whole education relies on wave ansatz on a F or beta plane. So in some way, I would always argue that the spectral world is a kind of world in which we educate future meteorologists. So, and you are right, in the models, how then we have to make you know, the understanding how to transfer these diagnostics, spectral diagnostics, back to the prediction models. Actually, we are just revising the paper for quarterly journals, which describes the model which is using half harmonics as basis functions. So in such model, we do have half harmonics. We do forecast half harmonics. So in such framework, this you know, this decomposition and diagnostics is of course great tool, but how to go from this to your I don't know, volume or spectral elements model? It's yeah, it's not yeah. I guess it's the main question.
I think Matt raised an interesting question, and for everyone here, we started from Halton's dynamics, and we think in terms of WKB, and then we move to the real world, and then we see forecast problems, and we think about the physical problems, but I think these are two different useful useful angles to think about forecast error problems, and the most diagnostic framework gives just one angle of thinking of the problems in terms of normal modes.
And for example, in data assimilation, we are still making use of that idea originally introduced by Phillips, that we think of forecast errors in short time range, in the same way as we look at the dynamics linearly, as again in the wave as a you know, wave components, and this exactly this framework of normal modes or half function decomposition was the basis of the early work at ANSEP for the development of the data assimilation modeling. But then, of course, it was very hard to that was exactly your question, Haiwan, what to do with unbalanced modes. And this was this has always been problem, how to initialize these modes. So this is really the main question. Yes, one can linearize with respect to more realistic background state, but then the solutions may no longer be stable.
Well, they could be. I mean, you can certainly construct, I mean, this is what I do. You can construct linear non-normal models that are stable, and they do an excellent job of forecasting. They do as well on subseasonal timescales, not on daily. But subseasonal timescales, they forecast as well as VCM. So I certainly take the point that one can use fairly simple linear approximations. I think the question is, what kind of linear dynamics or what kind of linear modal dynamics here do you want to be representing? And I am struggling with how you would relate a normal system that you're using with a non-normal system that I'm more familiar with. And the non-normal linear dynamics is still linear. It doesn't have to be nonlinear. It can be, but obviously it doesn't have to.
It's a great point. For example, in the tropics, I mean, our understanding of tropical circulation is still largely based on the linear eigensolutions of equatorial on equatorial beta plane or Matsuno's solutions, right? And it's only maybe last 2 decades that scientists discover or diagnose, for example, using frequency wave number, they diagnose these signals in fields like outgoing wave radiation, and this is all linear. I'm not actually aware of tropical dynamics, of research in tropical dynamics, in wave dynamics. I mean, there is, but not much about nonlinear interactions, wave or triads.
So it is 3 minutes past the top of the hour, and I would hate to hold you guys here any longer, especially you, Nedjeljka. So if we can carry this conversation offline, maybe that would be greatly appreciated. And I want to thank all of the participants for being on the line today, and especially for our speaker for giving us the talk today and the really great discussion that we had going on. And then also to Haiyan for organizing today's talk. So the next PPAI webinar will be on the theme of sea ice prediction with guest speaker Walt Meyer of the National Snow and Ice Data Center. And this talk is scheduled for November 18th at the same time. So we hope to see you then. So for everyone else, have a great rest of your day and thank you for participating.